All right, welcome to another laboratory activity. 2, 4, 6, 8. We're only missing 2. So today we're going to put into practice what we had in class yesterday. So we're going to be making 2 circuits and confirming that our mesh analysis that we learned in class yesterday gives the same results as we measured. So we've already gone through, I think in brutal detail, how to apply the mesh analysis and the rules. I should point out the numbers that I wrote down for the answers at the end of class yesterday turned out they were in error because of a transcription error. In drawing his circuit, he forgot a 0. And so all of his work was exactly right, but he had one number that was 3 instead of 30. And that does make a difference. Okay, so this is all the theory that you already should know. If you go in the folder for Physics 151, there's this spreadsheet in there. And in that spreadsheet, you have 2 different tables. And actually, let me just open that spreadsheet. It'll be the easiest way to show you how to use it. So my organization is a little bit different than yours. This is not the live one. So here's the general physics lab spreadsheet that we'll be opening up. And you've used this spreadsheet before, most notably in the first lab of first semester, I think you used it, or maybe it was the second lab. And so the Kirchhoff tab, see down here at the bottom we have the different tabs, resonance, energy, blah, blah, blah. The Kirchhoff tab has a 3x4 matrix for 3 variables and a 6x7 matrix for 7 variables. So you'll just put your numbers into the spreadsheet and make sure you put in zeros where they belong and whatnot because it's pre-populated with numbers. And if you put in your numbers, resistance in ohms and voltage in volts, then it should give you the current in milliamps. So you can use those if you don't want to put them in your calculator. If you want to practice putting them in your calculator, you can do that. Obviously, I say obviously, okay, for some reason the writing tools aren't popping up. Doing this here by hand is prohibitively hard. You would want to use some calculator to take your 6 equations and solve them for the results. If, when you do this, it doesn't give you matching numbers to what you measured, then you'll want to figure out which one has a mistake, your measurements or the calculation. So when you're doing the experiments, don't take your circuit apart until you have verified that your theoretical result matches your experimental result. Now, the only thing that I think really needs to be covered before you get started is, first of all, scientific method. We're not doing the scientific method portion this time. That's what that little paragraph says, is we're not doing it. You're using breadboards just like before. You'll need 6 distinct different resistors. That is 6 resistors, each with a different color code. So no 2 resistors with the same color code. Resistors are up here. Come and grab 6. Make sure the color codes are different. First, you're going to make this circuit. So circuit 1. Circuit 1 has, you have to answer things like how many essential nodes it has, how many meshes it has. Notice down here, identify all the essential nodes and meshes for each of them, and then it asks you questions about them. On your diagram, notice that I have labeled I1, I2, I3, R1, R2, R3, okay? Make sure you have written down R1 equals red, blue, whites, red, white, and blue. And then calculate what that should be. So that would be 6. That'd be 26 times 10 to the 9 ohms is the numbers I chose to get red, white, and blue. I probably would have been better to do something like blue, white, and red, something that's more reasonable in size. But have that, and then also measure the resistance. So with the multimeters that work, I don't remember exactly which ones work, but I think the 2 that are behind David are the ones that don't work. So you want to measure them as well as gain the color codes. And your question number 1 is for each resistor, do the resistance values agree with the advertised tolerance, so the number with its uncertainty. So that's just repeating a skill that you had to do last time. In, not triplicate, but 6 times, once for each of the 6 resistors. Then make your circuit, and in your diagram that you write in your textbook, so you should have a diagram that looks just like this, make sure that you indicate what direction you're considering the current going. So I'm going to just randomly draw arrows. So I'm going to draw this arrow like this arrow like this, and this arrow like this. Draw them in there. After you've drawn it, mark which side is positive and which side is negative. Sorry, I got to sneeze. Thank you for the preemptive blessing. So notice this is just what I've shown you in class. Why am I having you do this? For 2 reasons now. One is so when you go through and you apply your Kirchhoff's current law and Kirchhoff's voltage law, your directions are clear. Number 2 is for measuring voltage and current. So we're going to use the same current and voltage measuring devices as we did in lab last week. There is a downside to that. That is the current measurements of this have a big uncertainty. I'm going to plug red into the plus for current, black into the minus. So I use these to measure voltage, right? The ones that come out of the end. On my actual circuit, I want to take these, and for the voltage probe, I just leave my circuit as is, and I connect it up so I have the red lead on the one that I have labeled as plus, and the black lead on the one that's labeled as minus to measure voltage. So the way you have your current labeled dictates the way you connect this. And if you get a negative number, what do? No, you write down the negative number. What that means is that the current's going the other direction, but that's not a problem. You stick with what you did, and you just have a negative number for the direction you showed. Now for the current, these 2 here are for measuring current. Remember, the voltage is the voltage across, the difference in potential energy per charge. Current is how much goes through. So if I'm measuring current, so I'm just going to go to the second figure, and I'm going to arbitrarily say that my current is going like this through this one. If I want to measure the current through resistor 2, I need to physically break my circuit. I need to make a disconnect on one side of the resistor. So I'm going to choose Sarah because she's closest to me. Where should I break my circuit here? There's 2 choices. Choose which one you would use. Before the resistor. Okay, she said before the resistor. So I am going to break my circuit right here. I pull that side of the resistor out of the board. And so now I have this here and this here are 2 places that are broken. There's no connection between them now. And I patch that break with my current probe. So remember I put the red in positive. It's going to measure positive current if the current goes into the one that's positive and comes out of the one that's negative. So into the red, out of the black. So based on this current arrow, I need the current to go into red here and go out of the black and continue on. So I need to have my red here and my black here to measure the current. Zoom way in and throw an A in there. So keep in mind, I broke the circuit to measure current. And then I patched the circuit using my ammeter. And the direction is important. If you switch the direction, it's going to switch the sign. But the sign is an important thing. So as you're going through this, before you power up your circuit, make sure you have either Andrew or me look at it just to make sure we don't have a significant problem. And then you're going to need to measure the voltage across every element. Now, let me zoom back out. How many elements do I have in the upper circuit there?
3, right?
I have 3 resistors, but not 3 elements.
4 elements.
4 elements. I have the power supply and 3 resistors. So I need to measure the voltage across each one of those and the current through each one of those. Now, when you measure the current, if you do it wrong, you can mess things up. Do not take your current meter and connect it across the power supply. Don't put your current meter like this. Because if you do that, it's going to take the resistance of the current meter is virtually 0. It's very small. And so it's going to take all of the current that power supply can supply and try to put it through this thing. And it will damage it. Yes?
So if you say don't do that, do you mean like don't attach it to either side of the battery? Or
Don't attach it to both sides.
to both sides of the battery?
Right? If I want to measure the current through the battery, I've got to disconnect it on one side of the battery and patch with this. But I'm patching where I disconnected the wire, not going across my power supply.
What do you mean by attaching? What does that look like?
Okay, so let's pretend this is part of the circuit. So I have these 2 things connected together.
Okay.
I want to measure the current that's going through this wire. So I break it apart and I patch it so that it's reconnected but going through
Something else.
my meter now.
Okay.
So now the circuit's complete again, but it has my meter in the middle of it. So you have to take the circuit apart and put the meter there in the circuit where you broke it. Okay, second picture. How many elements are in the second picture?
6.
6. Why did I tell you to get 6 resistors? I don't know, because there's only 5 resistors. You only need 5 resistors, not 6. I apparently counted the power supply as my 6 when I said to get 6 resistors. Okay, so you only need 5 resistors. There's 6 elements. Make sure you measure the current through your power supply, the voltage across the power supply, current through each one of the resistors, and voltage across each one of the resistors. Final thing before I tell you to get started. Notice currents are labeled. Current 1, current 2, current 3, current 4, current 5, current 6. What is different about current 6 than the other currents?
It has no resistors on
It has no resistors there. That means when you're doing your mesh equations, you're not going to have current 6 in there. But it still has a direction, and it's still going to show up in your Kirchhoff's current law equations. So don't say, oh, that's not important. It is still important. You do need to still measure it.
So current 6
Claudia.
on, sorry. Current 6 on there, which one? Is it R or I?
Current 6 is the current going through the power supply. Current 6 is marked right here.
Okay, it's I.
Yeah, I is current.
Okay, perfect. Thank you.
All right, so, I should have said this already. When you make your circuits, like I really tried to emphasize last week, lay out your resistors so at a glance you know what is what. Right? You should actually have them laid out so it looks like an H here with your resistors. So if you come and ask me, is this connected right? I can look at it and I will know automatically, this is resistor 1, this is 2, this is 3, and I can check it without having to trace too carefully. Right? That having it logically laid out makes life quicker. All right. Have at it.